Can I start?
Tak. Z obsługi, żeby nie wnosić naczyń z płynami innymi niż czysta woda.
Niż czysta woda. No dobrze, ale jak już wniosłem.
Przekazać?
A tak, publiczności. Okej, dobrze, bo to daje zły przykład, ale jako mówca mam prawo. All right, so I have some announcements. One is that tonight we have this lecture by Sabrina, open lecture at 6 p.m. So please come as well. It will be not in this lecture hall, but the next one, which has number 03, the first one here on the ground floor. That's one announcement. Another one is that there is a request from those who take care of this lecture hall not to bring liquids other than water to this lecture room and no food. So please try to do that. Okay. So yeah, it's my last lecture, and I will continue following what I said yesterday. This is just the reminder. It was the statement, it was this OPE the complete OPE that I wrote between two primary fields. It turns out that it is possible to write it to all orders, and then you can express this product in terms of not only primary fields but other descendant fields. So this superscript here denoted descendant fields. And if you know this formula, it enables you to write correlation functions of descendant fields as well. Here is this space-time dependence on Z, and this is fixed by just these terms. And the important information, the crucial information, is just given by these coefficients, which involve structure constants, 3-point structure constants. And then some extra pieces which are fixed by conformal invariance and which depend on just the weights of the operators and the central charge. So this dependence is, you may say, universal for all CFTs. And if you have a given CFT, then the crucial information is encoded in the structure constants. So in a sense, what I've been presenting before was showing that indeed we have this universal dependence, and we can compute, at least in principle, all correlation functions in 2D CFTs. And you might ask now how to find these object structure constants, or possibly also the weights in a given theory. If you know them, then in principle you might solve the theory completely. And this is what I'd like to mention now in the beginning part of this lecture, and after that I will discuss some examples of CFTs more explicitly. So there is the whole program of finding this data that defines the theory, and this program is referred to as conformal bootstrap. So I will briefly sketch what is the idea behind that. Of course, I will not be very general, but I will focus on 4-point function. Of primary fields. phi I. And as I already did before, I will use global conformal invariants to fix positions of 3 of those coordinates. So I will take z4 to be 0, z1 to be infinity, z2 to be 1. And then such a 4-point function depends, after this fixing, on one parameter, which is x. Or in fact, sorry, before this fixing, this 4-point function depends on one cross ratio, which is this one. But after fixing that, I can express everything just as a function of x and x bar. So this 4-point function I'd like to discuss now using the notation we also used yesterday. Can be written in the following form. I mean, I could write it as expectation value between vacuum states of these 4 fields, but using now definition of these states which I introduced yesterday, I can write it in the following way. So these 2 primary fields phi 2 and phi 3 appear explicitly, and phi 1 and phi 4 are encoded in the states H1 and H4. And well, now I will write some statement which I will not prove. That would take too much time, but this is quite important statement, that this 4-point function can be written in the following form. Which follows from taking OPEs of certain operators which are under this expectation value. Let me write the formula first, and maybe then I discuss this a bit more. So here the structure constants appear. They arise from taking OPEs of relevant relevant operators according to the indices which are here. And then there are certain pieces which are also universal. In a sense, they also depend in universal way on weights or the central charge. And they are called conformal blocks. So this is a bit similar like in that top blackboard, in a sense that information about this 4-point function depends on this specific information for a given theory given by structure constants, and then on some universal function which there is also not explicit formula for that. You have to compute it by hand up to some order if you are interested in, but this can be done to any order you want. So let me write what this f is. Here is sum over all this vectors case. And here is some expectation value which needs still to be computed, which involves in particular Virasoro generators. So this is still not very explicit. But, well, what is important is that it involves in particular this functions beta, which I already had there. And you can think of this as a series in X with some coefficients. So let me write it also just in the following form. And, well, I will just give one example. The coefficient f1, the first non-trivial coefficient, takes the following form. So you see that it depends only on those weights. So in that sense, the form of this conformal box is universal. And again, the fact that the structure constants appear here follows from taking OPE of certain operators under that expectation value. And now, this bootstrap is the idea. That's right, thank you. So this bootstrap is the idea that you can get some additional constraint, which you may say follow from associativity of OPE, and namely taking, this is called different channel, so choosing different way of taking OPE under this expectation value. So you may write the same 4-point function, but in a bit different way, taking different OPs, and then whatever you get should be also equal to what I have already written. And then this gives some extra constraints which are well, not so obvious from the beginning that they exist. Sorry. So, well, you have to think a bit. I will not discuss all details now, but I leave it as an exercise. You may change the order of those phi's, and also then you have to change appropriately where you, well, how you fix those coordinates. So in this case, relevant identification is as follows. And then taking this OPs in some other ordering gives the following relation. Which I can also write in terms of conformal blocks using well, the second line here. And this can also be represented graphically. This is some picture which you might see somehow in the spirit of Feynman diagrams. Namely, this conformal block. Let me now write it even a bit more generally using arbitrary indices, not 1, 2, 3, 4, but more general ones here. You see that this F depends in some way on these 4 labels that denote certain conformal families, but then there is extra label denoting conformal families that appear in the OPE. And, well, these extra ones arise from taking OPE with family 2 and 1 or 3 and 4. So I will schematically just represent this these conformal blocks by the following graph, where this P is like an appears in some particular channel. This is how people say that, of taking OPE. So this is a graphical representation of this left-hand side, and there is analogous one for the right-hand side. Where you have, so to say, a different channel.
Probably in the second structure constant there should be LK in this system.
Here.
Yes. Because M index is repeated. And
LK, yeah. So you see that these external legs are labeled by N, L, M, K, here and here, but the way they are well, contracted is different, and it represents the way you make OP. And of course, much more can be discussed about all this, but I don't have time for that. But let us just make an obvious counting looking at this equation. I will still write that this gives a set of constraints on CP, on the structure constants and weights HP, at least assuming that we know the form of conformal blocks, which is universal in that sense that I mentioned. And in particular, let's assume that we have now some theory which has finite number of primary fields. For finite number of primary fields, let me write this number as n. We get n to the power 4 constraints, n to the power 4 because we have these 4 free indices n, m, l, k, and then each of them can take any value out of this set of n. So we have n to power 4 constraints on these parameters c and h. So there is n cube c's, because they have 3 indices, and if we assume there is n conformal families, then each of them has corresponding weights, so n cube plus n weights. So this is this crucial statement. Which suggests that if everything is consistent, you should be able to solve that equations because there is for, well, high enough, but it does not to be very high. And there is more constraints than, there is more constraints than parameters you want to find. So, well, one possibility would be that this is not possible to solve and everything is inconsistent because there are too many constraints, or maybe these constraints are so nice that they indeed enable to solve that. And this is indeed what happens, of course, as you might expect, because otherwise I wouldn't be giving these lectures. So, this is the idea of this bootstrap program. Of course, I was very brief and sketchy, and there are many more details, but I think it's important to get that idea.
Yeah. Can we make sense of it in the limit of infinite number of those primary fields? Or is it
Yeah, there is another manifestation of all that, and you can make sense of that, which also then it leads to some differential equations of these multipoint functions, which I will unfortunately not be able to discuss, but there are also constraints for that. What? Here? I mean structure constants and weights. There are n-cube structure constants and weights, which are parameters you want to find. So now, in the remaining time, I will discuss now various examples of conformal field theories, and the first class of examples I want to mention are those which indeed have finite number of primary fields. So this is also not obvious that such theories exist, but they do. So yeah. Again, in what follows, I will discuss various examples of CFTs, in particular having various central charges. Okay. And I will of course do that, but before I give these examples, I will write one more remark related to unitarity. So the examples of the theories I will discuss are theories which are unitary, and it also makes contact with the question that Jerzy Lewandowski asked in the first lecture, if he is around. Okay, so I think this is this will be somehow the answer to the question you asked a few days ago. So let me first tell you what this unitarity means. A representation of Virasoro algebra is unitary if it contains no states of negative norm. Such states are often called ghosts. And if they would exist, they would imply that certain probabilities are negative, which we would like, at least in principle, to avoid, even though sometimes they are allowed. So the absence of such states implies certain conditions on central charge and weights, which in a sense give some constraints on possible CFTs. So again, I will just discuss one simple example. One can make much more complicated analysis, but just consider the norm of the state, which is obtained by acting with Virasoro generator L minus n on the state, which I denote by H. Now I will ignore H bars to save some space. So the norm would be given in the following form. To compute that, you can use now Virasoro algebra relations, and you can try to write these two operators in opposite order using Virasoro algebra. Then you can do that, but you get some other operators from this algebra on the right-hand side. In particular, a piece which contains the central charge. So again, I'm just writing the result, but you can do this exercise for yourself. So now this term with Ln, with n positive, this is annihilating H, just by definition. So you are just left with these two terms, and H is acted on by L0, whose eigenvalue is thus H. So you get 2NH plus the second term and the norm just of H, which you may assume this is positive. And then you see that for this state to have a non-negative norm, this implies that C cannot be negative, because if C would be negative, then for large enough n, we can consider, or we should consider, all possible n's here. Then for even for nh, but for large enough n, the whole this whole bracket would become negative. And on the other hand, if you take n to be 1, then the second term drops out, and you see that then this means that H itself should be positive. So it follows that the necessary condition, of course, this is just one set of conditions, there might be other for other states. But necessary condition for unitarity is that central charge is positive and this weight H is also positive. And you can make more detailed analysis, which I will skip, but I will tell you what it implies. So it implies that if central charge is greater or equal to 1, and the weight H is positive, then such representations of Virasoro algebra are unitary. Well, they are non-unitary for C smaller than 0, and in this range, for central charge between 0 and 1, and also for positive H, there is in fact just a discrete set of unitary representations. And these representations can be combined to theories which are called minimal models which have finite number of conformal blocks. So of course these conformal blocks correspond to some representations that's from this discrete set. So coming back to this blackboard, this assumption that the number of conformal families is, not conformal blocks, but conformal families. So this assumption that there are some theories with finite number of primary fields, or in other words, finite number of conformal families, indeed is fine in a sense that such theories exist, and these are these minimal models, which are unitary theories with this range of central charge. And by the way, just as a side remark, there are also non-unitary minimal models, which also have central charge in this range, but let me not discuss them. Let me just focus on these minimal models which are unitary. Okay, so now I can finally go to examples. And the first class of examples I will mention are these unitary minimal models. So you can make, as I mentioned, more detailed analysis starting from looking at such norms and then asking which representations are unitary, and it is a bit lengthy, but the outcome is that these minimal models are theories which have central charge of the following form. So M labels a given theory. There is infinite number of such theories. Each is labeled by M, and M is a positive integer starting from 3. And in a theory with the following central charge, you have a number, the following number of conformal families, which have the following weights. It is convenient to label them by 2 integers, and these weights also can be expressed in terms of n. And then these parameters P and Q are in the following range. P is between 1 and n minus 1, and Q is between 1 and P. So then you can see that indeed the number of those pairs P and Q allowed by these relations gives us this overall number of conformal families. So this is this infinite family of minimal models. And in particular, if you take the smallest possible m, namely m equal to 3, then you can quickly compute that you get central charge C equal 1/2. And this theory is referred to as Ising model, because this indeed reproduces various features of Ising model known from statistical mechanics. If you take m equal 4, then you get central charge to be equal 7/10. And, well, this relation to statistical mechanics arises for all models in this family. So there are indeed various statistical models which you may think of as generalizations of Ising model, which correspond to these models that I am discussing. So in particular for this central charge 7/10, you get what is called tricritical Ising model. For m equal to 5, the central charge is 4/5, and this corresponds to so-called free state Potts model, and so on. And in particular, the relation to the statistical models is such that these theories I am discussing now, they describe the statistical models at criticality, so at conditions corresponding to some phase transition, because this is the situation where conformal invariance arises. So there is no length scale in a model. And in particular, the relation is the one which I also very briefly mentioned already in one of the previous lectures, that the weights of these representations encode so-called critical exponents in this model. So critical exponents are some numbers which also encode the form of correlation functions in these models. And just to have some idea, I will briefly mention one example. So let me focus now a bit on this Ising model. So I hope you have heard of that. This is the model. In 2 dimension, I consider square lattice with spins at each side of the lattice. So I have spin I denotes the side of the lattice, which is plus or minus 1. I may, apart from the spin, I may introduce interaction energy of neighboring spins. So I will denote it by epsilon I. This is just the product of sigma I and sigma, and well, let me denote schematically neighboring side by I plus 1. So we can see this can be 1 or minus 1. So depending on the configuration of spins, you increase or decrease the energy. And then total energy of the system energy of some particular configuration of all spins is given, of course, by the sum of all nearest neighbors. We have these energies, so sigma I, sigma j. And we can also add extra term in case there is some external magnetic field. And then just the total spin. So what is known or what people would like to compute is the magnetization of the system, so expectation values of sigma j, which is either 0 for temperatures which are greater than some critical temperature, or this is non-zero and takes some specific value for temperatures which are lower than this critical temperature, and this is quite interesting what is happening in this critical point. So you can also compute more complicated expectation values than just this one. Which have some particular dependence on a distance between operators that you consider. And at this critical temperature, they are known to take the following form. If you take two spins, let me write sigma n, so this is at some position n, and sigma 0, this is known that it behaves like 1 over n to the power 1 over 4. And you may also compute such expectation value for these energy operators. This is known that it behaves like 1 over n square. So these critical exponents are, roughly speaking, these powers here. In fact, in statistical physics, there are a bit more detailed definitions what they are. So you can look them up yourself. But anyway, I mean, there are some combinations of those powers. For Ising model, they take the following form, and critical exponents are some numbers which are related to this by some shifts, which I'm not going to write in detail here. Okay, so let me now count the non-trivial operators in this theory. We see two of them, namely the spin and this energy operator. And in fact, there is the third one in each theory, at least from this class of 2D CFTs. We have also identity operator. Of weight 0. Which you can also identify in this statistical model somehow. So we have three non-trivial operators, and this agrees with this number of conformal families. If you take m equal 3, then this number is also equal to 3, as this cancels, and you get just this thing. So it turns out that this identity operator, spin operator, and energy can be identified with three primary fields of, well, let me write it as CFT Ising model. And moreover, we can now look at the weights which are given by this formula. So the statement is such that if you now make identification with this CFTs, this correlation function should behave like 1 over n, and then to the power, which is the sum of weights h sigma and h sigma bar. We assume that the operators we consider are spinless, which means that their weights h and h bar are equal to each other, and with well, extra 2 here. And similarly for energy operator, this should be equal to n to power 2 times h epsilon plus h epsilon bar. So you can check whether this is indeed true, namely whether the weights which are given by this formula, which should appear here, whether they reproduce this result which are known from the Ising model. And, well, of course, this is so. So for spin operator, it has the weight h. It corresponds to P and Q being equal to 2, both of them. So if you plug P to be 2 and Q to be 2 and M to be 3 and see what it gives, what you get is 1 over 16. And this is the same for h bar. And indeed, so if I now look at this exponents, 2 times 1 over 16 and 1 over 16. This is, the bracket is 1 over 8 times 2 is 1 over 4. So this agrees with what we know from like statistical mechanics. And for energy operator, this corresponds to P being 2 and Q being 1. So if you plug these values, you obtain h equal to 1/2. And then indeed, the sum of these weights, 1/2 plus 1/2, this is 1 times 2 is equal to 2, which reproduces what we know here from statistical mechanics. So this shows that such an identification of this 2D CFTs with certain statistical models can be made, and this is one reason why all these CFTs play a role in statistical mechanics and condensed matter physics. And finally, one more remark regarding just the Ising model is that now thinking of also more other types of theories. You see that these theories are a bit special. There is finite number of families, and you don't quite maybe have an idea how to think of that in terms of field theory. But for the Ising model, when the central charge is equal to half, it happens that this is also a central charge for free fermion theory. So then you can write the Lagrangian for a free fermion and do all the analysis I made in the previous lecture, but explicitly for free fermion. You may find that it has central charge C equal 1/2, and there is indeed a certain duality between this free fermion theory and Ising model. And in fact, this duality underlies the original solution of Ising model you might have heard of. By Onsager. This was quite an achievement. Who indeed solved that using free fermion formalism. Okay, so even though I will not discuss this free fermion anymore, it is important to have in mind as another example of CFT that such a free fermion theory has central charge 1/2. Okay, so having said that, we see that we have some examples of CFTs with central charges smaller than 1. In particular, yet another theory which has central charge 1/2. So let me now go a bit higher in the values of the central charge and discuss a theory which has central charge equal to 1. So it already does not have finite number of conformal families, but infinite one. And this is, well, I hope, very familiar theory of a free boson. So in the remaining time, I will discuss some features of free boson theory and then also mention something very briefly about theories with C greater than 1. And I hope that 10 minutes would be enough for that. Yeah. Oh, from this formula, right? All the formulas are for those. Oh, sorry, you mean P and Q? Well, so for Ising, you see that M is equal to 3, so P must be between 1 and 2. And Q must be, again, between 1 and P. So possible values are such that P is equal to you may have P equal to 1, and then Q must be between 1 and 1, so Q must be equal to 1. Or P may be equal to 2, and then Q may be equal either to 1 or may be equal to 2. These are all possibilities. So then you plug it in this formula, you see what weights you obtain, and you see how you should identify them so that you reproduce this exponent. So I told you what is h to 2 and h to 1. Another possibility is h11, p equal 1, q equal 1. If you plug it here, what you get is that h is equal 0, and then you know that you should identify with this identity operator.
For a given central charge less than 1, are these rational CFTs unique, or you can have multiple for
well, there are some dualities between them, or equivalences in this sense. Like, is this what you are asking, or?
Yeah, like, is it always true for all the central charge, or?
No, I think it's more general. There are some cases where there are dualities, but the theory is not specified just by central charge. There is also this other data which specifies that you need to know weights and then also the structure constants. So in some cases there are dualities, but central charge is not the only quantity which specifies the theory. Okay, so let me now discuss free boson from the perspective, well, of course, 2D free boson from the perspective of CFT. I'm sure you have seen the analysis of this theory on various occasions, but it's good to be aware how it is related to everything I've been discussing this week. So let me consider this theory on a cylinder to start with, which has circumference L. So I assume that phi x plus L is the same as phi at position x. If so, then I can write Fourier expansion of this phi well, we have two delicate chalk here. So x dependence is in these coefficients, and then phi n depends just on t. And you can define this theory by the actional Lagrangian. G is some coupling So this is the standard free action. Of course, then you can make all standard field theory stuff, namely you find conjugate momentum. So I'm not, of course, making this calculation. You might have seen that, and you should know how to do them. So the momentum conjugate to phi n I denote by pi n, and it turns out this is equal to GL phi dot minus n. And then you can write also the Hamiltonian. If you know Lagrangian, you know conjugate momenta. Then Hamiltonian takes the following form. And if you want to consider quantum theory, then one approach is that you impose commutation relations. Between those phi n's and conjugate momenta, which are of the following form. Okay. So this is kind of very standard so far. You should also recall that if you have these operators in quantum theory, phi and conjugate momenta, you can redefine them in such a way that you form creation and annihilation operators. So I will define them as follows. They are just some combinations of phi n and pi n with relevant coefficients. So here is phi n and here is I phi minus n. This is for n greater than 0, and we will see in a moment that these are annihilation operators. And for n smaller than 0, these are creation operators. And similarly, for n bar, they are given by analogous formulas, but instead of phi n, you have to take phi minus n. Okay, so if you define such operators, you can also make one nice exercise, namely to compute their commutators, and what you find are the following expressions. So you see that this an and an bar are decoupled. Okay. And now, instead of expressing everything in terms of x and t, I will introduce complex coordinates, as we've been doing this week. So let me rewrite various quantities in terms of z, which is exponent of 2 pi t minus ix over L, and then z bar, which is exponent 2 pi t plus ix over L. So I will start with the expression for phi, this one, in terms of this. It takes the following form. I still use this pi 0 here for a moment. Here is log. But here I have this A and A bar. Operators. And so you have now such a field, quantum field, with holomorphic and anti-holomorphic part. You might wonder whether this is primary, but in fact this is not a primary. However, it turns out that its derivative is a primary field. Well, if I write extra I here, then I del phi of z makes the following form. This is sum over all n's now. And instead of this pi 0, I just define a0 and also a0 bar to be pi 0 divided by square root of 4 pi g. So this is one important information, that this is a primary field. And you can also compute energy momentum tensor in this theorem. Which you should also be familiar with this expression. This is given by normal ordered product of phi z, del phi z with itself. So this also makes contact with the question which arises, one, that in principle energy momentum tensor is expressed by the fields of a given theory. So this is of course here. And you can also now express it once you know this expression for 5 in terms of a's. So you can write this energy momentum tensor in terms of A operators. This normal ordering, of course, means that you put annihilation operators to the right. Okay. And if you know this expression, then you can see what are the modes of T, which we defined earlier. So you have to pick up relevant powers of Z and look at their coefficients, and then you see that Ln is given as follows in terms of this annihilation and creation operators. So this is for n other than 0, and then L0 is equal to, well, also the following combination of ANs. So if you know the form of Ln's, you can check what commutation relations they satisfy, and indeed, of course, writing their commutation relations then will require you to use these commutation relations for all those AN modes. And of course, what you should find should be Virasoro algebra. Well, I should say, of course. And then from the form of this algebra, you see that central charge is equal to 1. And you may also write the Hamiltonian, which I had here, in terms of this operators, and then you find quite simple expression, namely Hamiltonian is 2 pi over L. This is just identified with L0 plus L0 bar. So you may remember that this L0 was dilation operator, which is consistent with what I've been discussing before. Okay, and the last 2 minutes, I will tell you what are primary fields in this theory. They are related to certain ground states. So let me define a ground state alpha such that this is annihilated by ANs for positive n's, and it has eigenvalue alpha when you act with A0 or A bar 0. If you know how ANs act on that, then you may also compute how LNs act on that. So you get that Ln acting on alpha is 0 for n greater than 0, and the eigenvalue of L0 in this case is alpha squared divided by 2, which means that we may call alpha a highest weight state or primary state of weight alpha squared over 2. And then you build the whole Fock space by acting on these alphas with other A operators. All right. And the last statement I give is that these ground states alpha, they are in fact created by primary fields. Which take form of vertex operators. And they are given by normal ordered exponents of this bosonic field with the extra coefficient here alpha. So you see that there is infinite number of such primary fields in a theory. So alpha is given just by acting on by this vertex operator on the vacuum, as also I was discussing before. So these are primary fields of weight H alpha equal H alpha bar, which is alpha squared over 8 pi g. Okay. Well, I think I should stop here. But I hope that in these examples you see these various ingredients like explicitly, which appeared before, and whatever I was discussing before was quite general. I didn't have explicit expressions for like energy momentum tensor. I just discussed some general commutation relations. But here in this example, you can realize them in terms of the modes of these bosonic fields, those creation and annihilation operators, and AM. What I will not discuss anymore, but let me just write this thing, that for C equal 1, we obtain, in particular, one interesting theory, which is called U theory. which looks like a deformed theory of a free boson with certain extra potential. Yeah, and in that theory you can also find, this is a very rare example, you can find structure constant in that theory. The 3-point amplitudes exactly, they are given by so-called DOZZ formula, but I don't have time to discuss more, but if you want, I can say it in a break. So that's important achievement that if, this is non-trivial theory where structure constants can be find exactly for primary fields, which also take form of vertex operators. So primary fields in Liouville theory take analogous form like this expression, and you can write the structure constants. Oh, all right. I think this is all I can say in this time we have. So I may answer some question if there is some. Yeah.
So in this discrete case, could you, in principle, take any statistical mechanical system and try to do this conformal framework?
Well, I'm not sure about such a statement. What I know is that you take one of these theories in this series, you can find relevant statistical model. But it may happen that there are more statistical models which are not described by them, or at least I'm not really sure.
Answering to that, I think the question is whether the critical point of statistical model you have only scale invariance or full conformal invariance.
Right.
And I think it's known in 2D that scale invariance implies conformal one. In higher dimensions, I think there are some counterexamples.
Okay.
Sorry, can you say anything more about unitary CFTs at C equals 0?
Well, can I say anything? I mean, well, you can, in fact, you can hook up more complicated CFTs by taking sometimes various ingredients altogether. So you can engineer some theory so that C is equal to 0 overall C, but it has various components which have non-trivial Cs. But you may, okay, one thing you may think of is that I erased that formula. Or no, sorry, no. You can think of interesting limit of these minimal models, but they tend to theory where C is equal to 1, not 0. Well, it is in a sense simple because this Virasoro algebra degenerates to Witt algebra, so there is no that input of C, and even these various expressions I was writing, when you drop out C dependence, they simplify quite a lot. I'm not sure I can say anything particular.
So in this case, there are somehow trivial unitary to the CFT with C0, but there are non-unitary interesting CFT which has 0 as unfortunately.
Okay.
Okay, may I ask?
Sure.
What would be the reason why we don't consider not unitary representations? Some physical insight, why would they be even of interest with negative none, like those flying around? What would those would be interpretations of those fields?
Well, goats appear in various physical contexts when you try to, when you work with gauge theories, for example.
Yeah,
so they
try to somehow eliminate them, right?
Well, so, but they are necessary. You want to eliminate them, but still they are there. So in that sense, you cook up, you add some ingredients to this theory to somehow fix this behavior, which you may not
so
want, but in principle.
We still want to eliminate them in the due process of trying to.
Yeah, but you need to understand how they
Sure. Okay.
behave. And there are also some critical statistical models, I think, corresponding to these non-unitary minimal models that are also there. So you also want to understand those.
And CCFT, famously non-unitary as well, so
Okay.
it's not sacred.
Yeah. Well, okay, I think this is a moment that I stop if there are no more questions. So thanks a lot.